Good morning. My name is Saloni, and I am your chemistry tutor today. We're going through A-level chemistry, and we're doing inorganic chemistry. So we're covering the shapes of simple molecules and ions today. But before that, I'd like to know how are you, and I hope you're all good. So tell me a bit about your day. Oh, that's lovely to hear. Okay, so I'm going to go through our learning objectives first and quickly run through them. So, our first one is to understand what is the VSEPR theory. This stands for valence shell electron pair repulsion theory. You don't necessarily need to know that and what it stands for, but you need to know that that's what we're using to name all of our shapes of different molecules and determine their bond angles, okay? And the next one is to be able to determine molecule shapes and bond angles given relevant information. Relevant information such as chemical formulae, or for example, being told that it has a certain molecule has three bonds, information like that. Last one is to recognize line dash wedge arrangements and draw these diagrams to show spatial arrangement of molecules. So line dash wedge is probably something you haven't heard before, is it? No. So I'm going to point you towards these diagrams here, and that's exactly what they are. Line dash wedge. So the line is used when it's on the plane. The dash is for when it's away from you, and the wedge is when it's coming towards you. So that's all the same in all of these molecules. The dash is always coming towards you in some sense, isn't it? And the wedges are always coming towards you, and the dashes are going away. So the actual point of this is that there's different bond angles in different molecules. Why, you'd ask? Because electrons, as you know, they all have the same charge, so they actually repel each other. So electrons are negatively charged, hence repel other electrons when close to each other, and they're near other electrons when in bond pairs in covalent bonded molecules, right? So in a molecule, the bonding pairs of electrons will repel other electrons around the central atom, forcing the molecule to adopt a shape in which these repulsive forces are minimized. Because the molecule wants to be in its most stable form, doesn't it? So it wants to achieve maximum separation and minimum repulsion. So it minimizes repulsion by putting the bond pairs further apart as they can be. So we're going to go into the next page and we're going to go through a few examples of these in a minute. But before that, we're going to go through just the different names of these. So the first one we have with two bond pairs, as you can see, is called linear. And this is just a simple 180 degrees out of 360 total, just half down the middle, and a simple molecule. The next one is trigonal planar. Three bond pairs and 120 degrees each. Again, simple. Now the next one is 104.5 degrees, the angle between the two bond pairs, and it's called bent or nonlinear. This is because it has two little secret lone pairs hiding there. And the next one, pyramidal, also has a secret little lone pair hiding there. And we'll figure out why in a moment and what sorts of molecules tend to have these sort of configurations. They both are actually a version of this molecule, tetrahedral, but without the bond pairs. So if you removed this X and this X, it would make a bent molecule. And if you removed only one X, it would make a pyramidal molecule. And the angle between them is reduced, do you see, by 2.5 each, as more lone pairs are added. Because lone pairs and lone pairs cause more repulsion. That's why. In this one, there's one lone pair, so there's a minus 2.5 degree bond angle, so they become a bit closer together. In this one, there's two lone pairs, which you can't actually see on this, by the way, I stress. We'll see them on the next page. And there's two here, that's why it's minus 2.5, meaning minus 5, making our bond angle 104.5. Our next one's a little bit more tricky, trigonal bipyramidal. I found this one the most trickiest to understand. This is when there's 5 bond pairs, and 3 of them will be arranged in a T shape, and one of them will be away from the plane, and one of them towards the plane, with 120 degrees between. And we'll look at a few of these examples too, later on. Last one is octahedral, which sounds a bit funny because you'd think there'd be 8 bond pairs, but I need you to remember that there's actually only 6, but it's more because it forms an octahedral sort of shape. If you think of it in a 3D plane. So this has 6 bond pairs and they all form a 90-degree angle between each other. Now we're going to go into the next slide. So our first example, have you ever heard of this molecule before? Can you try and name it for me? Boron Trifluoride. Fantastic, well done. Okay, so there's a central boron atom, and boron has 3 valence electrons. Do you know what valence means? We heard it earlier, didn't we? So, if you don't know, that's okay. Valence means outer electrons, and they're the ones that matter in terms of bonding, right? And so, boron has 3 outer electrons, and fluorine has 7. Boron's in group 3, fluorine's in group 7. Quick recap. And so, it can form 3 covalent bonds, can't it, with each fluorine, with the fluorine atoms, not each one. And that means that there's 3 bonding pairs that repel each other equally. There's no electrons left over, and there's 3 fill bond pairs formed. And that means in our dash wedge diagram, it would look something like this. Just a simple 120 degrees. And since it's actually trigonal planar, you can just draw it with lines too, but it's your preference. This would be correct either way, I'd stress. So BF3, this is it. You confident with that? Can you see that's an example of the 120 degrees? Yeah? Okay. Now we're going to do CO2. And this one seems a little bit more tricky, but I promise it's not. And so this is a carbon dioxide. And we know that carbon dioxide has double bonds, doesn't it? As you can also see by my diagram. So I've done C here and the O and the O. Can you tell me how many valence pair electrons or how many valence shell electrons does carbon have? Oh, that's right. Well done. And how many does oxygen have? 6. Well done. And so they actually form a double bond, don't they? And the double bond is treated the same as a single bond, as in it doesn't affect the bond angles or the shape of the molecule. So you treat it the same. And knowing that there's actually 2 pairs of electrons forming a double bond, same rules as usual. And so there's 2 overall bond pairs. And therefore, 2 bond pairs, 1 central atom, we know it's a linear. If we look back, check that, linear. And those are 180 degrees. Now we're getting the simple stuff out of the way. We're going to do something more tricky. We're going to look at an example of a bent molecule. So let's look at example 3 together. This is, what's the common name for this? Water. You definitely know that. Well done. H2O. So I've done my little diagram of oxygen in the middle, H on the side. And can you name what these diagrams here that I've used in the blue and red are? Dots and dot and cross diagrams. Fantastic. Yep, you should be familiar with them, especially for your covalent bonding. They're very useful. So we have an oxygen atom in the middle, and it has how many valence shell electrons? 6. Well done. And the hydrogens have 1. And therefore they form 2 double bonds. But how many outer electrons are left over on the oxygen? 4. Yes, 4. So they form 2 lone pairs and 2 bond pairs. So this is our bond pair. This is another bond pair. This is a lone pair. This is a lone pair. Lone pairs have greater repulsion than bond pairs. The greatest repulsion is between 2 lone pairs, and then a bond pair, lone pair, and then lastly 2 bond pairs. So 2 bond pairs together have the least repulsion between them. A bond pair and a lone pair have medium repulsion between them, and then 2 lone pairs have the maximum repulsion. So because of the fact that we have not just 1, but 2 lone pairs in this molecule, rather than having the normal configuration of linear, for example, you treat the lone pairs as if they were bonds, and thinking that there's, for example, 4 bonds in here, what shape are we going to be starting off with? Tetrahedral, aren't we? But in reality, we've got 2 actual bond pairs, so we take away these 2 x's, we're left with bent. And knowing the fact that there's 2 lone pairs, we know that we're going to have to do minus 2.5 and then minus 2.5 again from the normal bond angle of 109.5. So there's a reduction from 109.5 to 107, then 104.5 to form a bent little 104.5 degree H2 HOH bond angle. And can you see the lone pairs are going to be apart like this usually? And you can't actually see them in the molecule, of course, but this is hypothetically why they'd be how they'd be have maximum separation. Our last example we're going to do is ammonia, which is the NH3 molecule, right? Tell me how many valence shell electrons nitrogen has? 5, fantastic. And you know what your hydrogens have, 1. And now I'd like you to try and explain this one to me to the best of your ability. And I'll jump in where you need. Yeah? So you'd start off looking at 4 bonds in total. So you look at a tetrahedral sort of configuration, wouldn't you? Yeah, well done. And then, but you spot one of them as a lone pair, so you cross off one of the bonds, and you reduce it by 2.5, don't you? Because it's one lone pair this time. So it causes the bond angle to become 109.5 to 107. Fantastic work there, yeah. And could you tell me what this shape could be called if you remember from the last slide? No, that's okay. Let's look back. It would be an example of pyramidal. Yeah? And this can sometimes be called trigonal pyramidal, but pyramidal is good enough for that one. Now we're going to go into our last slide, and this is a little summary of how to actually work these out. So first of all, when you work out a shape, I want you to always state the number of bonding pairs and lone pairs of electrons. So if there's 2 lone pairs and 2 bonding pairs, you're going to know there's 4 in total, going to look straight at the tetrahedral shape. Then as you take away if it's 1 lone pair, you look at trigonal pyramidal, or pyramidal. And if there's 2 lone pairs, you know that it's going to be bent. So I want you to work methodically from the basic geometry, which is without considering lone pairs, and then determine, depending on how many lone pairs you have in your molecule, what shape it would be. And so if there are no lone pairs, I want you to say that the electron pairs repel equally, right? We agreed on that, and we talked about that earlier. But if there are lone pairs, we know that lone pair bonds repel the most, then lone pair, and then bond pair. So the greatest repulsion is between lone pair, which is the darkest here. And so you'd want to say that to achieve maximum separation, minimum repulsion, it would therefore have to form this certain shape. So for example, if we're talking about ammonia here, we'd say that the basic geometry of the shape would be tetrahedral. However, there is 1 lone pair, so it would form a trigonal pyramidal shape, and have 107 degree bond angles between the bond pairs to achieve maximum separation, minimum repulsion. And so that would be the shape and the bond angle of that shape. Generally, for your exam, as I stated before, all you need to know are these few angles and the shapes associated with them. So there's 7 different ones you should be very confident with. However, sometimes you can be asked to work out the shapes, not the shapes, but the configurations of more complex ones. And so here are a few of the more complex ones, such as seesaw, T-shaped, square pyramidal, and square planar. So I'll give you an example of what a square planar one could be, xenon tetrafluoride. And so that is Xe